Hello, everybody. Welcome to another Intelligence podcast. Today, I have a very special guest with me, Dr. Ibrahim Fathi, and I'm going to read his bio first, and then we can get started. We're going to talk about some really exciting topic called natural fracture mapping today. He's got extensive studies and research done on this, and I wanted to bring him on board to give us a presentation on that. So before we get started, though, I'm going to read his bio. Dr. Fathi is an associate professor of petroleum and natural gas engineering at West Virginia University. Dr. Fathi earned his PhD in petroleum engineering from University of Oklahoma. He's received the 2014 American Institute of Mining and Petroleum Engineering Award and SPE's Outstanding Technical Editor Award in 2013 and 2018. In 2016, Dr. Fathi published a book called Hydraulic Fracturing on Conventional Reservoirs. The second edition was also published in 2019. Dr. Fathi, he's got more than 20 peer-reviewed publications and 20 conference papers since 2016 and has been heavily involved in research on various aspects of unconventional reservoir development, CO2 sequestration, geothermal resources. In the past 5 years, he's been focused on the application of automated machine learning in real-time operations center, or RTOC, in the energy industry. With that impressive resume, welcome on board, Dr. Fathi, and welcome.
Thank you so much, Hoss, for the invitation, and thank you for the good introduction. Thanks.
Yeah. All right. Well, let's get right into it. I saw the topic and I've seen that presentation before, and I wanted to get you on board and to present to us. And thanks for accepting the invitation. So you can go ahead and share your screen and let's get right into this exciting topic.
Sure. Give me a second.
Here we go.
Okay, let me go to the full screen.
Yep.
And then, okay. So you wanted me to start, or
yeah. Let's get started. This is natural fracture mapping. He's got a new automated ML workflow. It's going to talk about like the workflow and show you some data and case study on it.
Sure.
Let's get started.
Yeah, basically, Haas, this is going back to a couple of years ago. We had a project with the Department of Energy, which is called MSEAL, Marcellus Shale Energy and Environmental Laboratory. Mm-hmm. So in this project, basically, we collaborated with a couple of universities, DOE, NETL, Natural Northeast Energy, and Schlumberger to build a science well, mm-hmm. in which we tried a good hand of modern well logs. We had the fiber optics, microseismics, and the whole thing was to see different aspects of unconventional reservoir developments. Mm-hmm. So, and the good thing about this project was all the data is available publicly to everybody. So if you just go to mseal.com, you can get access to all the information regarding the drilling, completion, production, seismic, fiber optics. Everything is transparent and available with the reports and the presentation, obviously. Mm-hmm. So we did have this project and we were working on that. And one of the major topics that we have been dealing in the oil and gas industry for many years is the natural fracture mapping. Mm-hmm. And we found that these natural fractures, they even have more impact in our unconventional reservoir developments, mm-hmm. especially in the Marcellus Shale, which basically we saw there are lots of natural fractures. These reservoirs are highly natural fractures, and there is a well interference effect that the wells were communicating through these natural fractures. So we wanted to really understand that. And this is not a new topic, and this, as I said, people have been working on this for many years. And the general way of dealing with the natural fractures was to use the discrete fracture network modeling, DFN, which has some sort of a stochastic nature to it, right? And people are using the cores, looking at the core samples and the fractures on the cores, on the thin sections, and the logs, and those kind of things. But still, we didn't have the good ability to map the natural fractures and confirm that using different source of information, right? So you can pick one source of information and then make some assumptions, generate the map, and then try to see what the impact would be. But here we wanted, since we did have this good information, we wanted to see how we can use all of these informations to come up with a good natural fracture system. And then we moved this to MCL2, where we drilled 6 wells in the Vargas pad. Again, all these are in Morgantown, West Virginia. And we tried to come up with a natural fracture system. Recently, we got involved with the 2 other projects. One is on geothermal, which we are again going to drill a well that's around 15,000 feet deep in, again, Morgantown, West Virginia. We are investigating the possibility of using geothermal to provide the energy for the university. And again, you are talking about the geothermal, the natural fracture system has a huge impact. So you need to have a good understanding of natural fracture system to basically optimize that energy deliverability of the well and the well performance. And the other project that we are involved with the DOE is on the carbon capture and the CO2 sequestration. Again, in that project, we see the importance of the natural fracture system because you are going to inject tons of CO2 and you want this to be confined in the reservoir. But depending on how much we inject, with what rate we inject, you just want to make sure that you hold the integrity of the reservoir. And to make sure that you can do that, you need to have a good understanding of your natural fracture system, because that's basically, those are the weak points. Those are the points that you might start having the natural fracture reactivation or even fault reactivation. And that basically generates the possibility of the leakage. So we see the impact of this natural fracture mapping in different areas. And we wanted to just see what's the best way of dealing with that. So you can look at this as a very local, like a near wellbore natural fracture mapping, or more regional in the pad or the region or in the basin. And this really depends on how much information you can collect from different wells to be able to correlate them. So this is basically generally what's going on. And that was the original problem statement, which didn't have anything to do with the machine learning. Obviously, we wanted to just use the fiber optics, microseismics, image logs, and to be able to do the natural fractures. But doing that, we saw that, after logging the well and getting these image logs, we have to send those back to the consultants for the log interpretation, right? And imagine we have more than 10,000 feet of lateral well, and whoever is doing these log interpretation has to sit down and go feet by feet of this lateral and then try to find the fractures, pick them by hand manually, and come up with the number of the fractures, the directions, and the depth. And these are like, we are humans, you might go like the first 1,000 feet, very good, sharp, but as time goes and as you try to pick more and more fractures,
that accuracy goes lower and lower.
That's something that you expect, right?
Yeah.
And so that was one thing that that really depends on the expertise, right? Who is doing that fracture picking, right? How experienced that person is and how he sees the images. Basically, there's a huge human interaction, right? And in addition to that, we're like sending these images, and it takes months for the expert to come up with that Rose diagrams, the nice images, and the number of fractures. But like after you're logging the well, you have at most a week, right, to go and do the completion. So, but you get those natural fracture system like months after you're already done with your completion design. So basically, there weren't any direct use, right, of those in the completion design. So we wanted to, we had these 2 problems, the time and also the human. And and then we wanted to basically see how we can deal with this. And one thing that came into the mind and everybody is now talking about is the machine learning, right? So we said, okay, let's try to do the machine learning. But again, coming to the area of applying the machine learning and different problems, specifically engineering problems like geoscience problems that we have, which involves lots of physics, right? We are not dealing with the data, which doesn't follow the physical rules. We have a lot of physics constraints that we need to make sure that these are included in the model. So that's basically where the physics informed or physics-based machine learning concept comes to the picture. So we wanted to make sure that the model that we are building is basically honoring the physics of the problem as well. And in that region, again, when you go through it, you see different people are using different machine learning techniques. Some people are basically very good in applying the neural network. And whatever problem comes into the mind, the first choice would be neural network. So they're trying that. Some people are good with the decision tree or random forest, and they're using that. So there was a bias in picking the machine learning technique. And then inside the machine learning itself, as you know, we have parameters, we have tuning parameters, we call it hyperparameter, right? How many layers, how many neurons, what kind of activation function, like all those things that we need to pick and modify to come up to have the best model. Again, these are bringing more uncertainty into our model. So we wanted to somehow reduce that as well. So searching and then looking at more recent publications, we found that there is this automated machine learning concept, especially the tree-based pipeline optimization, TPOD, that's been out there, and people are using that. So we started investigating that model, and then we found that generally it's a library of many different machine learning workflows and algorithms that's going to try, the model is going to try those and basically finds the best pipeline to apply. And then it also performs some sort of hyperparameter optimization using the random search or discrete search. So we tried to take that, but the problem was during the process of the automated machine learning, there are processes that the technique takes, like crossover or mutation, in which some of the features will be eliminated or some of the features will be replaced, where in that process, we don't see the machine to take into the account the physics of the problem. So some of the features which are important for us as a petroleum engineer or geologist might not be important, seems to be important for the machine. But we want those parameters to be there because these are the parameters that they carry the physics of the problem, right? So we needed to do some tuning on the pre-processing part of the TPOD, and also during the processing. We know that for example, when you are doing the optimization, most of the time the models, they try to eliminate the error. They try to honor the observation data or the label that you pick. But we know in the geoscience, we just don't want to have the observation data to be honored. We also have some external knowledge about this process. Like we know there's a meander, there's a channel, there's a teeth zone in this area. So we want to include those external knowledge to the problem as well, right? So in the optimization technique, we also try to bring that into the problem by splitting the objective function into two parts. One part that we are using to honor the observation data, and one part which we are basically including our external knowledge that we have regarding that problem. And basically we are weighting these two, and there's more discussion on the technicality of how this can be done, but this is basically the essence of it. So we try to bring the physics of the problem. We try to make this automated, which means we wanted to have the model, the workflow to pick the model itself from the library of different models and then perform the optimization. and then on the hyperparameters. And again, there are lots of literature and publications out there which they prove that picking the hyperparameters are actually most important than picking the model itself.
Yeah.
Right. So how you optimize those hyperparameters has a huge impact on the success of your machine learning technique.
Wow. Yeah.
And for that, the teapot didn't seem to be strong in that region. It uses a random search and the grid search. So we tried to bring the Bayesian optimization, which is a basically directive optimization, which basically use the results of the previous step on your hyperparameter optimization and use that results in your next move of optimization.
Yeah. It's a sequential type of algorithm. Yeah.
Yeah. Instead of the random search, basically you're randomly picking these features, or the grid search, right?
Also, they're very time consuming, like grid search and randomized search. Those are very time consuming. Sometimes it takes, depending on your
domain size and number
data set, like how many rows and columns you have, it might take, days, or, so this like the Bayesian, it basically it is an algorithm that intellectually selects the next step, which is pretty powerful. Yeah.
Yeah. So that's the objective. We had the problem statement, having the natural fracture locally or globally using different information. And then it turns out to be very biased through the human expert. And then trying to bring the machine learning, we had these two problems. We tried to alleviate those as well. And we wanted to reach to some sort of optimum condition. So that's the whole essence of this project. And for that, what we are going to use is we are going to use the new acceleration data, like drilling acceleration data. And we are going to use that to find the fracture intensity. But for that, we wanted to minimize the amount of expert involvement in image analysis. So instead of having, let's say, 11,000 feet of well being interpreted, we wanted to see, can we just have only 1,000 feet and use that to label our data, and then use the machine learning to do the rest or not? So that's the whole project.
I see. Okay. Good stuff.
Good.
Yeah.
So just a quick background on the data that we are using, in case you guys wanted to go and check. The data that I used is for the biggest path, that's MCL2, and in which we had 6 wells. Can you see my cursor?
Yeah, we can see it. Yeah.
So we had 1H, 3H, 5H, 9, 13, and 17H. These are zipper frac inside out. So basically 5 and 9 is zipper frac, and then 3 and 13, and then 1 and 17. Okay. Mm-hmm. So we had the permanent fiber optics installed in 5H. Mm-hmm. And then we have a cable and the 1H fiber optics deployed, which we just monitor the DTS, basically that's a distributed temperature sensing, and DAS, distributed acoustic sensing, and DSS, which is the distributed strain sensing of the activities while we are fracking 5H and 9H. So with the retrievable fiber optic cable, we are monitoring a 5H and 9H stimulation, but 5H does have a permanent fiber optics, which we monitor other wells stimulations. Okay. So the quick information regarding the wells. So the TVDs are around 8,000. The lateral length more than 10,000. So we have 12, 13, 12,000. Number of stages 63, 66. So around like 200 feet of stage spacing.
Yep. So,
and and then the well spacing is around 750 feet. So very tight.
Tight wells, yeah.
And then we did have the PetroMars FracView tool, which we ran through all the logs, all the wells, except the 17H. These are basically acoustic image logs, where this is the interpreted logs, and these are the raw information. And basically you see that the whoever is doing the interpretation has to go through this log and try to find these sigmoids, right? Which are shown in this figure, like these events. These are basically the presentation of the fractures, right? And then he counts those, and depending on the angle, he shows where the depth is. So this is basically the image that we collected from all these wells. We send this to the consultants, and they come up with the fracture picks. Okay.
Got it. Got it. Okay. Okay.
When we have that, then this is a very nice dashboard. This is been prepared by Dr. Panetta, and geology department. He's an assistant professor. And what he did, actually, this is very nice. I haven't seen this in any one of the commercial softwares. He basically generated the dashboard using Python. And again, this dashboard is also available on the MSeal website.
Where you Dr. Fatty, is this using Plotly and Dash in Python?
Yeah.
Right? Okay.
Yeah. He used the Plotly Dash in Python, and then he included all the wells with their trajectories. He included the microseismics, which you can turn on other microseismics. You can look at every well, the plugs, where the plugs are, and then the fracture intensity logs, the gamma ray log along every one of the laterals, you can turn those on. So with all that information, what basically we did, we started looking at the well interference, basically. So here what you see is a fracture intensity log. So this is what's been interpreted by the geologist, by the consultants from the image log. So they come up with the fracture intensity. They show how the fracture intensity will change across this lateral. So we see those, like the hot colors are the highly fractured zones.
Yeah.
And then we have the gamma ray across that. So we have these, so we know which zones are highly fractured, right? And then while, let's say, we are fracking 5H and the 9H, right? We are monitoring the DAS and DSS on the 1H. DSS is actually, it's like a strain gauge, right? It basically measures the displacement of the rock, right, at that location, while you are fracking 5H and 9H. So when I'm fracking stage 1, I look at my DSS information collected from 1H in that specific time, and I see, can I see any displacement? If I see any displacement, that means this fracking in this well will have some impact on well 1H. And then what I would do, I would say, okay, now that I see the displacement, does this displacement, can I see that displacement using the microseismic? Does microseismic shows the same thing or not? And then if the microseismic shows me that there is an event in that direction and in that location, which is matching with my DSS, and in that location that I have this movement, I have a high fracture intensity zone, then basically I can connect the dots, right? I have a displacement, the microseismic shows it's there, and it's a very highly fractured area. So connect the dots. So this is basically how we went along all these 11, 12,000 feet of lateral when we are completing every single one of these wells. And from there, here in this table, for example, you are looking at the 9H stage completion well, and the frac hits on 1H. For example, 9H, at what locations and what stages we did see that frac hit, or which is collected through the DSS, confirmed with the microseismic and fracture intensity log. So these are basically zones. So the 9H and 1H, they have around 2,250 feet of distance, right? Every well has a 750 feet distance. So that would be the distance to the 9H to 1H, which we'll see some impact on stage 10, 13, 15, 17, twice, 53, 56, and 57. Okay. So we did this, and then we were talking when we were sharing the information with our consultants, and some of these impacts was picked by them as well. And these are the ones which are basically along the hydraulic fracture direction, and which is basically your maximum horizontal stress. Basically these lines that you can see, right? all these parallel lines. But in addition to that, we did have some impacts. For example, when we were fracking stage 20 of 9H, we did see the fracking in stage 14 of 5H. Mm-hmm. So this was a huge change and huge direction change in the fracture. So the question was if this is real, because remember, we are doing this as a zipper frac, and they were thinking that this might be a pump event. But what we did, we went back and we looked at the 5H microseismic. So we went back to the stage 14 of 5H and we looked at the microseismic events. So on the 5H, we did see the microseismic, which shows the direct relationship between the stage 14 and 15 of the 9H. But in addition to that, we did see the fiber up the microseismic events close to stage 19 and 20. Remember, at this time, stage 19 and 20 are not fracked, right? We are fracking 14. But we do see the events in 19. And when we come to the stage 19 and we try to frac 19, then we see the events going back to 14. So this basically confirms that those events are real events that have been picked. And then basically we did this for the whole field, and that's the way that we generated this natural fracture map for the whole field. And when it's done, basically we were like discussing, and then we sat back and we saw that, hey, most of these fracture intensities and highly fracture intensity zones that we picked are coming from the image log interpretation. So that's our basis. We use that to say which zones are highly fractured, which zones are not. And going back, we saw that we sent this August 5H image logs to the two different consultants. And these two consultants are professional, has been around for many years, worked on many image logs. But when they come back with the results, for exactly saying, well, one consultant gave us the number of 6,363 fractures, while the other gave us only 1,475.
Wow, that's a huge difference, yeah.
That's a huge difference in number of fractures, right? It's like 4 times more fractures picked with consultant A in compared to consultant B.
Yeah.
It's not just the number of fractures. You can see the directions are different too, right? So the directions are different, the number of the fractures are different, and we're using that as a ground truth to do our analysis.
This shows the like, I guess the subjective opinion of each of the consultants, and that's where the auto ML would come in, right? That's
basically where and as I said, this took a couple of months. So we said, okay, maybe this is because we have like 11, 12,000 feet of log. Like if you give just 1,000 feet to any consultant with a high professional, they could just pick the fractures with less error. Yeah. And in a much faster pace, right? That we can use it on a real time. So that's basically the problem is identified. And now that we have a problem, we go and try to see what type of machine learning can be used to solve this problem, right? Yeah. So, and I think that should be the way it goes. Like you have a problem and then you try to go and see what tools are available and you can use it for this, instead of having a tool and trying to find a problem to solve it, right?
Yeah. Just Dr. Fathi, just to clear for the audience, so the goal here is to try to predict fracture intensity, right?
Yes.
From drilling vibration data, and you're going to go through some of the assumptions and everything else, right? Okay. All right.
So what we try to say, we say, hey, all these analysis that we did is comprehensive, good, but they are based on this fracture intensity identifications. And we wanted to see, is there any other source that we can use to come up with these fracture intensities that can eliminate this huge human bias and the time and the money?
Yeah.
And that's basically where we saw that the Petromore neighbors, they have this tool which basically measures the drilling acceleration with a very high frequency. We did have this drilling acceleration information with the low frequency before, but with the new tools, it's a very high resolution that basically collects the shock, in XYZ, vibration in XYZ, in addition to the conventional ROP, RPM, weight on bit, gamma ray, stuff like that. So we wanted to use that, and we wanted to use partial labeling from the image logs and then train the model and see if it works or not. And for that, as I said, we're gonna to avoid to get into the bias of the machine learning model selection or hyperparameter optimization selection. We basically use this automated machine learning offered by the teapot. And then we did a couple of corrections on that. And for the hyperparameter optimization, as I said, we were used basically the Bayesian optimization to.
So just to be clear, for the hyperparameter optimization, you the default in teapot is grid and randomized search. You replace that with Bayesian optimization, right?
That's correct.
Okay.
That's correct. And then obviously we had to do some feature engineering. Basically, we tried to look at the cross correlations, heat maps, and this is basically the Parsons correlation coefficient. Just remember, this just shows the linear relationship between the parameters. And we tried to eliminate the parameters which are highly correlated and shrink the number of the features. And then
what cutoff did you use for your Pearson correlation coefficient? Was it 0.9?
Yeah, anything above 80%, we assume that to be highly correlated.
Okay.
And yeah, and then kept the rest. And then basically what we did, as I said, we did change the pre-processing part of the teapot. Basically, we included the statistical description of every feature. Yeah. We included the cross correlations obtained for every feature into the model. And we also modified the optimization technique. Okay. And then we tried, okay, let me go to the next slide first. And then we try to see first if this is gonna work or not, right? So as a proof of concept study, we first used the classification approach. We said, let's divide this fracture intensity to the high fracture intensity zones and low fracture intensity zones, right? Just two groups. Yeah. And then let's use our RPM, ROP, gamma ray, vibration, shock information. Yeah. And let's see if we can use the fracture, if we can predict the fracture intensities in two classes. So the optimized model obtained from the teapot turns out to be the key nearest neighbor with this set of the hyperparameters. We got a very high accuracy model.
On your input features, what does UT stand for again?
That's the travel time.
That's the travel time. Okay, so you use travel time, RPM, rate of penetration, gamma ray, and also use the vibration and shock in the extraction from the vibration tool.
Yes.
Got it. These are the inputs, and the output was fracture intensity, which you did a classification. So between 0 to 0.5 was one class, and like greater than 0.5 was another class.
Was another class, which basically comes from the distribution of how the fracture intensity looks like. For the ground truths, we use the interpretation from consultant A, because we did have a QuantoGeo log in MCL1. And from the QuantoGeo log, the interpretation of the consultant A was more in line with the directions of the QuantoGeo that we had in MCL1, which is very close to the MCL2 site. So we used that for this study as a ground truth. And then when we saw that the model is working fine with the classification, we moved to the regression. We said, okay, now it's we know this physics can be captured with the machine learning. Let's see if we can just predict the whole fracture intensity log of the well.
Dr. Fathi, to give the audience some perspective, can you go back to that previous slide? How long did it take to run the auto ML on this classification data set, and how much data? Can you give us some perspective on how much data was used and how long it took for the auto ML to go through the process?
It really depends on what machine you're using. We did use the on a regular desktop, it took 4 or 5 hours.
Okay. That's limited CPUs and just
with the limited CPUs. to complete the general. And we did try this to just not do any pre-processing and just run it by the teapot. It takes much longer time, around like 9-10 hours. But after that engineering, pre-processing, and then the modifications that we had, we could able to get this run much faster. And then when we compared with the accuracies, which is again, the first part of this is published in the Fields, Journal of Fields. And we did see that pre-processing that we didn't include any bias in the model. It just helped the model to reach the optimal solution faster.
And before we go to the next slide, some audience might not have that much background in confusion matrix. Can you define this confusion matrix for them?
So basically, this is the class of high, and this is the class of low fracture intensities. And basically, this is the true high fracture intensities that the model predicted to be true. And this is the true fractures that the model predicted to be false. So, and the same for the other classes. So the summation of these two diagonals, 61 plus 37, is basically the total accuracy of the model in predicting both classes.
Very high.
And this is basically the error on that.
Very low,
very low error. And then we did the error analysis on this. Basically, all the errors were distributed for the regression model around the 0. And so we did perform the error analysis as well. And then coming to the regression model, again, we performed that. And then we, again, got the very high accuracy. But remember, one of the other objective was to eliminate the amount of data required from the expert on a label. And here basically try to shrink the training size. And then we found that with 10 to 15%, even less than that, we will be able to train a model that can predict the fracture intensity log. And remember, this is just the first 10 or 15%. So we didn't pick randomly through the labeling, because we just wanted to say, okay, if we do the log interpretation on the first 1,000 feet of this 11,000 feet log, can I use that 1,000 feet label to train the model? One of the thing was, hey, if you go to that 5% or 15%, do you see the whole spectrum of the fracture intensity, right? Because let's say if you pick the first 1,000 feet, and in that first 1,000 feet, you just have a very low fracture intensity, then basically you cannot train a model based on that. You just need to make sure that the training size that you're picking basically covers the whole spectrum of whatever the objective function, in this case, fracture intensity is. And here, basically, we're showing that like the difference between the 5% and the 15% of the data picked for the fracture intensity, and both of them, as you can see, will cover the whole spectrum of the fracture intensities. So that's basically one of the key points, because if you just pick a first 1,000 and you don't have it, then obviously most of these machine learning techniques, these are good for the interpolation, right?
Not good for extract, yeah.
So that's that. And then we found that, for example, for this case, we had total of 27,000 recording. So the resolution here is 0.1 feet.
0.1 feet, okay.
Yeah, and then out of that, we just picked around 4,000 feet of records, and then trained the model and deployed that. Again, the optimized model and the optimized software parameters are found as such, and then we got a very small error. And again, as I said, in this case, the 85% of the fracture intensity log was a complete blind. So we just picked the first 15,000, we trained on, validate and tested on that 15%. And then when the model is validated, we just deployed that on the rest of the 85%. That's basically what you see here as a prediction, quality of the prediction on the complete blind set. And in conclusion, basically what we did, we used this automated machine learning workflow. We did modifications on both the pre-processing and the optimization algorithm to make that some sort of a physics-based or physics-informed. And we reduced significantly the amount of log interpretation required by the expert. So almost tenfold. So basically, you can assume that how much we will drop in cost and the time required for this log interpretation. So with this, it makes it feasible for real-time predictions and real-time application, near real-time. As I said, you have about a week to complete this and have it. So in that time frame, we will have the information required. And for the future work that we are working right now is to be able to perform the whole image log analysis using the machine learning. Basically, when we have these images, these acoustic image logs, can we train a model that basically goes through these images and tries to pick these sigmoids and gives us the fracture dimensions? So instead of the expert trying to come up with these, can I just use that 10% label and perform the machine learning to come up with the rest? So if I can do that, then while I'm doing the logging, I can also have the solution. And for that, there are two different techniques we are using.
Yeah, deep learning, right? Like convolutional
and the computer vision. So two different approaches to.
It's pretty complex, yeah.
Yeah. And hopefully next time,
Yeah, next time I'd like to bring you back on, talk about deep learning, how you deploy deep learning and computer vision to get that to get those FMI logs interpreted. That's pretty awesome. That's pretty awesome.
As I said, this work is again supported by the DOE, and this paper is presented in carbon capture, utilization, and storage past month in March in Houston.
Perfect. Yeah, no, great stuff. We appreciate, thanks a lot for the presentation. This was very informative. Sure. Very informative, very thought out process. But yeah, so I think that concludes today's podcast. With that, I'd like to thank Dr. Fathi. If you have any questions, concerns, we're going to put the contact information in the comments in this YouTube video. You can contact us for more information. But with that, thank you so much for tuning in, everybody. We'll see you guys next time. Thank you, Dr. Fathi. Appreciate you.
See you. Bye-bye.
Thank you.